To begin to understand the temperature of the universe, we must first unlearn what our senses have taught us about the nature of heat. On the surface of our planet, temperature is a tactile language. We learn it through contact. We feel the warmth of sunlight on our skin, the searing heat of boiling water, or the biting chill of a winter breeze. In our daily existence, heat is an exchange transaction between our bodies and the heavy blanket of air that surrounds us. It feels like a substance, a fluid that flows from hot objects to cold ones, seeking a balance. But this perception is merely a local illusion, a byproduct of living at the bottom of a thick, pressurized atmosphere. To a physicist, heat is not a fluid, and it is not a substance. It is motion. It is the chaotic, invisible vibration of atoms and molecules. When we say a cup of coffee is hot, we are really describing the microscopic violence within the liquid. The water molecules are thrashing against one another at tremendous speeds, colliding, spinning, and vibrating. When we touch the cup, the kinetic energy is transferred to the nerves in our fingertips. We register this transfer of molecular violence as warmth. Conversely, a block of ice is cold, not because it possesses a quality of coldness, but because its molecules are lethargic. They are locked in a rigid structure, shivering only slightly. When we touch the ice, the heat from our own hand flows into the block to encourage its molecules to move, leaving our skin drained of energy. This is the definition of temperature. That governs our lives, the average kinetic energy of matter. It relies entirely on the presence of things, molecules, particles colliding with one another. But as we leave the surface of the Earth and ascend through the layers of the atmosphere, the crowd of molecules begins to thin. The air becomes less like a soup and more like a mist. By the time we reach the Kármán line, the boundary that separates our atmosphere from the beginning of space, the distance between individual gas molecules stretches into miles. Here we encounter the fundamental paradox of the cosmic void. If temperature is the measurement of vibrating matter, how can we measure the temperature of a place where matter essentially does not exist? Imagine, for a moment, a perfect box, a cube with walls that allow nothing to pass through. If we use a pump to suck every single atom of air out of this box, we create a perfect vacuum. Inside, there is no air to vibrate. There are no water molecules to collide. There is absolutely nothing to push against the thermometer. If we were to place a standard mercury thermometer inside this perfectly empty box, you would technically not be measuring the temperature of the space inside, because there is no medium to transfer heat to the glass bulb. The concept of hot or cold air vanishes because the air itself has vanished in the vast expanse of the universe. This is the prevailing condition. Space is not truly empty, but it is an approximation of emptiness so profound that the human mind struggles to scale it. In the tenuous drift between the stars, the density of matter is unimaginably low. On Earth, a sugar cube-sized volume of air contains quintillions of atoms. In the interstellar medium, that same cubic centimeter might contain only a single atom. In the deepest voids between galaxies, you might travel for light years without encountering a substantial particle. In such a desolate environment, the kinetic definition of temperature, the dance of atoms, begins to lose its meaning. If you were to float in this void, you would not be touched by a cold wind, because there is no wind. There are no rushing molecules to steal your heat away through conduction. You are an island of energy in a sea of nothingness. And yet, astronomers and cosmologists speak with great precision about the temperature of this void. They tell us that space is cold, specific, and measurable. To resolve this paradox, we must shift our perspective from the temperature of matter to the temperature of radiation. We must stop looking for the vibration of atoms and start looking for the vibration of fields. The vacuum of space may be depleted of solid mass, but it is awash in a different kind of ocean. Light. Since the dawn of time, the universe has been flooded with photons. They stream from the searing surfaces of stars. They pulse from the accretion disks of black holes, and they drift as the ancient, stretched remnants of the Big Bang itself. These photons travel through the vacuum unimpeded. Unlike atoms, they do not need to collide to exist. They simply propagate, carrying energy across the dark gulfs of the cosmos. When we speak of the temperature of space, we are actually speaking about this bath of radiation. We are asking a hypothetical question. If we placed a perfectly absorbing object, a black stone, perhaps into the deepest, darkest corner of the universe, far away from any star, what would happen to it? At first, the stone would radiate its own internal heat away, glowing in infrared light, shedding its energy into the dark. It would cool down, dropping from room temperature, past the freezing point of water, past the freezing point of air, but it would not cool forever. Eventually, it would reach a floor. It would reach a point where the energy it loses to the void is exactly equal to the tiny, faint amount of energy it absorbs from the background light of the universe. The stone would stop cooling. It would come into equilibrium with the environment. The temperature at which the stone stabilizes is the temperature of space. It is not the temperature of the nothingness, but the temperature of the radiation that permeates the nothingness. This distinction is crucial because it separates the cold of the void from the cold of a winter day. The cold of space is not a substance that penetrates you. It is a lack of incoming energy. It is a state of profound thermodynamic isolation. When we look at the dark gaps between the stars, we are looking at regions where the energy density is so low that a physical object, left to its own devices, would have to shed almost all of its motion to match its surroundings. However, the journey to determining this precise temperature was not immediate. For centuries, the void was simply assumed to be cold, a concept without a number. Without the ability to measure the faint radiation that fills the silence, early scientists could only guess. They imagined space as a frozen ether or a simple absence. They did not yet understand that the void itself carries a thermal signature, a specific fingerprint of energy that dictates the baseline reality of the cosmos. To understand this cold is to understand the baseline state of reality. It is the canvas upon which all hot things, stars, planets, living beings are merely temporary splashes of paint. The universe is not a place of fire with pockets of cold. It is a place of freezing silence with rare, fleeting sparks of heat. The default condition of existence is the chill of the vacuum. As we prepare to measure this chill, we must first understand how energy moves when there is no matter to carry it. We must understand the behavior of the lonely object in the dark. If space is a vacuum, and a vacuum is an insulator, why do things get cold at all? Why doesn't the heat simply stay trapped inside the object forever, like coffee in a thermos? The answer lies in the only bridge that connects the island of matter to the ocean of void, the photon. Every object in the universe, from the burning surface of a blue supergiant to the humblest grain of sand drifting in the asteroid belt, is engaged in a silent, ceaseless conversation with the cosmos. This conversation is spoken in the language of light. Physics dictates that any object possessing a temperature above absolute zero, which is to say, every object that has ever existed, must emit energy. The atoms within the object vibrate, and as they oscillate, they disturb the electromagnetic field, sending ripples outward. We call these ripples thermal radiation. On Earth, we rarely notice this phenomenon because the conduction of air overwhelms it. If you stand near a block of ice, the air chills your skin faster than the radiation can interact with you. But in the vacuum, radiation becomes the only voice that matters. A stone floating in deep space is like a lonely lighthouse in an infinite dark ocean. It glows. It may not glow in the visible spectrum that our eyes can detect, but in the infrared, it is a beacon. It sheds its internal energy in the form of photons, casting them out into the void. Once a photon leaves the surface of the stone, it travels forever, or until it hits something else, billions of years later. This is the mechanism of cooling in the vacuum. It is not a theft of heat by the surrounding cold. It is a voluntary surrender of energy by the object itself. The stone cools because it is throwing pieces of its own energy away, one photon at a time, and receiving almost nothing in return. This imbalance brings us to the true definition of the temperature of space. If space were truly, absolutely empty, a void, with no matter and no radiation, it would have no temperature at all. It would be undefined, a null value in the equation of reality. But because the universe is filled with the ancient light of creation and the light of countless stars, space acts as a thermal bath. Imagine a thermometer floating in the deepest, darkest region of the intergalactic void, millions of light years from the nearest galaxy. There are no stars nearby to heat it. There is no gas to warm it. It is as isolated as an object can be. Yet, it will not drop to absolute zero. It will be bombarded by a faint, omnipresent drizzle of photons. These photons are the effective temperature of space. They strike the thermometer, imparting a tiny, specific amount of energy. when the thermometer cools down enough that the energy it radiates away exactly matches the energy it receives from this cosmic drizzle, it has reached the temperature of space. This is a profound shift in how we perceive the environment of the cosmos. We often think of space as a cold container, a refrigerator that chills whatever is placed inside it. But a better analogy might be a quiet room filled with a very soft, very low hum. The cold is not a force that presses down on you. It is simply the level at which the background noise sits. The temperature of space is the floor of the universe's energy. It is the baseline hum of existence that remains when all other sources of heat are removed. This baseline is uniform, whether you are in the shadow of the moon, drifting between the stars of the Milky Way, or floating in the immense chasm between galaxy clusters. This temperature varies only by microscopic fractions. It provides a universal standard, a cosmic datum line against which all other heat is measured. It suggests that the universe, for all its violent supernova and blazing quasars, is fundamentally a cold, quiet place. The fires are the exceptions. The cold is the rule. However, recognizing this cold requires us to abandon our terrestrial instincts about danger. On Earth, extreme cold is aggressive. Falling into a freezing ocean is a crisis of seconds and minutes. The water molecules, dense and hungry for heat, strip the energy from a human body with ruthless efficiency. The sensation is immediate shock, but the cold of space is passive. It does not attack, it waits, because the vacuum lacks the density to conduct heat. The process of reaching this cosmic baseline is agonizingly slow. If a human were to step unprotected into the void, they would not instantly freeze into a statue of ice, despite the temperature being hundreds of degrees below zero. Without air or water to touch them, their body heat would have no direct path to escape. They would remain warm for a surprisingly long time, their body struggling to radiate its energy away through the inefficient channel of infrared light. The vacuum acts as a perfect insulator, trapping the heat within the body even as the universe outside sits at near absolute zero. This counterintuitive reality reveals the dual nature of the cosmic environment. It is simultaneously the coldest place imaginable and the best thermos ever conceived. The temperature is incredibly low, but the cooling power is incredibly weak. This distinction is vital for understanding the engineering of spacecraft, the life cycles of stars, and the history of the universe itself. Things do not cool down because space touches them. They cool down because they are alone. As we look out into the night sky, we are not looking into a dark, cold hole. We are looking into a bath of ancient stretched light that defines the thermal history of the cosmos. The darkness is not empty. It is filled with a temperature that has been falling for 13.8 billion years. It is a fossil of the energies that once were dot. To understand this better, we must descend further into the mechanics of heat itself. We have defined the temperature of space as a balance of radiation. But what defines the floor? How low can this temperature go? To answer this, we must leave the vastness of the intergalactic void and journey into the microscopic world of the atom. We must explore the absolute limits of motion, the point where the vibration of matter ceases and the universe holds its breath. We must understand the destination that the cooling universe is slowly, inevitably approaching. The concept of absolute zero, the journey from the warmth of a star to the chill of the void, is a journey of energy dispersal. But the journey from the chill of the void to the theoretical floor of physics is a journey into the quantum heart of matter. It is here, in the definition of stillness, that we truly grasp what it means to be cold. There is a pervasive image that haunts our collective imagination regarding the vacuum of space. It is a scene replayed in countless films and novels, etched into our minds as the ultimate consequence of exposure to the void. In this terrifying scenario, a hull breaches, or a helmet shatters, and the fragile human form is instantly transmuted into a statue of ice. We imagine the cold of space as a flash-freezing weapon, a force so aggressive and overwhelming that it snaps the fluids in our cells into crystals in the blink of an eye. We envision the warmth of life being sucked out with the violence of a vacuum cleaner, leaving behind a brittle, frozen shell drifting in the dark. This imagery, while dramatic and visually arresting, is a fabrication. It is a projection of our terrestrial fears onto a cosmic canvas that operates by entirely different rules. The reality of the vacuum is far more subtle, and in many ways, far stranger. If you were to find yourself floating unprotected in the shadow of the Earth, drifting in the silent expanse between the stars, you would not instantly freeze. In fact, for a considerable amount of time, you would not feel cold at all. To understand why, we must look closely at how we lose heat here on Earth. Our intuition about temperature is formed by our immersion in a thick, restless atmosphere. We live at the bottom of an ocean of air, and this air is a highly efficient thief of energy. When you step outside on a frigid winter night, the sensation of cold is immediate. This happens because the air molecules colliding with your skin are moving slower than the molecules of your body. In the chaotic scrum of atomic collision, your skin transfers its kinetic energy to the air. The air heats up, rises, and is replaced by fresh, cold air, which steals more heat. This cycle, known as convection, acts like a conveyor belt, stripping warmth from your body and carrying it away into the atmosphere. Water is an even more efficient thief. If you plunge into a freezing lake, the dense packing of water molecules conducts heat away from your skin 25 times faster than air. The shock is instantaneous because the medium surrounding you is aggressively absorbing your energy. Our fear of freezing is actually a fear of conduction and convection, the rapid transfer of heat through a physical substance. But space is defined by the absence of substance. In the vacuum, there is no air to steal your heat. There is no water to conduct your energy away. There is no wind to chill your skin. If you were cast into the void, you would be suspended in a profound nothingness. The conveyor belt of convection has stopped. The bridge of Kadushin has been burned. You are physically isolated from the thermal environment of the universe. In this situation, the vacuum of space acts not as a freezer, but as a supreme insulator. It is the ultimate barrier to heat transfer. The emptiness that surrounds you is incapable of absorbing your body heat through contact, simply because there is nothing there to make contact with. You are, effectively, inside the walls of the world's most perfect thermos. Consider the design of a vacuum flask, the kind used to keep coffee hot or water cold. These vessels are constructed with two walls of glass or steel, with the air sucked out from the space between them. We use these flasks because heat struggles to cross a vacuum. The hot liquid inside stays hot for hours, not because the flask is heating it, but because the vacuum refuses to let the heat leave. The coffee is trapped in its own thermal isolation, cut off from the outside world. An astronaut in space is the coffee, surrounded by a vacuum that stretches for billions of light years. A human body or a spacecraft is hermetically sealed against the loss of heat by conduction. This creates a counterintuitive paradox. Despite the background temperature of space hovering near absolute zero, the immediate danger to an object in a vacuum is often not freezing, but overheating. The human body is a biological engine. We are constantly burning fuel, sugars, and fats to maintain our internal structure and function. This metabolic fire generates a significant amount of waste heat, roughly equivalent to a 100-watt incandescent light bulb. On Earth, we shed this waste heat effortlessly into the air around us. We breathe it out. It radiates from our skin. The breeze carries it away. We are unaware of how much cooling work the atmosphere performs for us every second of our lives. In the void that 100 watts of thermal energy has nowhere to go, it begins to accumulate. Without air to carry it away, the heat generated by your beating heart, your firing neurons, and your working muscles remains trapped within your tissue. If you were floating in a spacesuit that lost power, effectively cutting off its cooling systems, you would not feel the icy bite of the cosmos. Instead, you would begin to feel a rising, stifling warmth. You would feel the fever of your own metabolism. The cold of space would be visible in the distance, a theoretical number on a chart. But your lived experience would be one of suffocation by your own energy. This reality governs every aspect of space exploration. When engineers design satellites, telescopes, or habitats, their primary thermal challenge is rarely keeping things warm. It is figuring out how to dump heat into a universe that refuses to touch them. The International Space Station, for instance, is not wrapped in blankets to keep the astronauts from freezing. It is equipped with massive radiators, giant panels, designed to maximize surface areas, specifically to shed the waste heat generated by the electronics and the crew. Without these active cooling measures, the station would essentially bake itself, even while floating in a dark environment hundreds of degrees below zero. The silence of the vacuum, therefore, is also a thermal silence. It disconnects an object from its surroundings. This isolation means that temperature changes in space occur in slow motion. If an object is hot, it stays hot for a long time. If it is cold, it stays cold. The instant freezing of the cinema is a physical impossibility because heat has no vehicle for a rapid exit. However, heat does eventually escape. The insulation of the vacuum is perfect against conduction, but it is not perfect against radiation. As we established, every object emits light. The body, the spacecraft, and the star all glow in the infrared. In the absence of air, this faint glowing becomes the only mechanism for cooling. It is a slow, lonely trickle of energy leaving the system. Imagine a ceramic mug of hot tea placed on a table on Earth. Within minutes, the air steals its heat, and the tea becomes lukewarm. Now, imagine that same mug floating in deep space, shielded from the sun. It would not cool in minutes. It would take hours, perhaps days, for the tea to radiate enough infrared photons to drop to a freezing temperature. The heat would have to leave atom by atom, photon by photon, bleeding out into the darkness in a slow, agonizing desaturation of energy. This slow-motion cooling changes our perception of what cold really means in a cosmic context. It is not an event, it is a destiny. It is a gradual slide toward equilibrium. The vacuum does not crush the heat out of you. It simply waits for you to give it up, piece by piece. This passive nature of the cosmic cold creates a unique environment. For matter, it allows clouds of gas to retain warmth for eons. It allows planets to hold on to their molten cores for billions of years, shielded by the insulating nothingness of the solar system. The vacuum is a preservative. It is a protective wrapper that keeps the universe from equalizing its temperature too quickly. If space were filled with air, or water, or any conductive medium, the stars would have burned out long ago, their heat drained away by the hungry medium. The universe would be a uniform, lukewarm soup. Instead, because space is an insulator, we live in a universe of sharp contrasts. We have searingly hot stars burning next to freezing voids, separated only by the inability of heat to bridge the gap. The vacuum maintains the boundaries. It allows the fire to exist alongside the ice. As we dwell on this concept of insulation, we must also consider the limits of the human machine. We are fragile sacks of water, designed for a very specific thermal band. We panic at the thought of the cold, but in the vacuum, we are the hottest things for thousands of miles. We are anomalies of heat, and while we will not freeze instantly, the laws of thermodynamics are patient. The vacuum may be an insulator, but it is also infinite. It has an endless capacity to accept the photons we emit. The process of losing this heat, of slowly succumbing to the background temperature of the universe, is where the true terror and beauty of the cosmic chill lies. It is a process that involves the shedding of our very essence or energy into a void that will never give it back. To understand this final fate, we must look at how the body eventually bridges the gap, how the thermos of the vacuum slowly leaks, and what happens when the internal fire finally runs out of fuel. To find the true floor of the universe, we must shrink our perspective. We must turn our gaze away from the vast, insulating vacuum of the cosmos and focus instead on the tiny, trembling islands of matter that drift within it. We leave the silence of the void to enter the deafening roar of the microscopic world. Here, in the invisible architecture of the atom, we discover the mechanical reality of what we call heat. If we were to look closely enough at the coldest stone floating in the deepest shadow of a distant galaxy, we would see that it is not truly still. To the human eye, a rock is a solid, unmoving object. It seems permanent and static, but this is an illusion of scale. To a physicist, that same rock is a chaotic ocean of motion. It is composed of trillions upon trillions of atoms locked in a rigid lattice, yet every single one of them is vibrating. They shudder, they twist, and they strain against their bonds. They are like a crowd of people packed into a tight room, shoulder to shoulder, constantly jostling for space. This microscopic jostling is the fundamental definition of temperature. Heat is not a substance that flows like water. It is a quality of motion. It is the kinetic energy of particles that refuse to sit still. When we say an object is hot, we are describing a state of high molecular violence. In a burning star, atoms are moving so fast they strip their own electrons away. In a cup of warm tea, water molecules are tumbling over one another in a fluid dance. Even in a block of ice, the water molecules are shivering in their crystal cages, possessing a specific amount of energy that keeps them in motion. To cool an object, therefore, is not to add coldness to it. It is to steal its motion. It is the act of dampening the vibration, like placing a hand on a ringing bell to silence it. As we extract energy from a system, the atoms become lethargic. The violent collisions soften into gentle bumps. The frantic spinning slows to a lazy drift. The shivering lattice of a solid begins to calm. This relationship between motion and temperature implies a destination. If temperature is motion, then there must be a point where motion stops. There must be a theoretical bottom line, where the atoms, exhausted of all energy, finally come to a complete and total rest. This point is the horizon of the universe's energy. It is the definition of perfect stillness. To map the journey toward this stillness, we cannot use the tools of our daily lives. The thermometers we hang on our porches or dip into our baths are calibrated for a human world, a world dominated by the behavior of order. We measure our days in degrees Celsius or Fahrenheit, scales anchored to the freezing and boiling points of a single chemical compound found on a single planet. 0 degrees Celsius is simply the point where water turns. To ice it is a biological milestone, not a cosmic one. To the universe, the freezing point of water is an arbitrary number, roughly 273 degrees above the true bottom. To understand the deep cold of space, we must adopt the language of the cosmos, the Kelvin scale. This scale does not start at the freezing point of water, it starts at the freezing point of reality. It begins at 0 absolute 0 and counts upward in increments of energy. In this system, there are no negative numbers. You cannot have less than 0 motion. You cannot be simpler than still. Let us descend this ladder of energy to see how deep the rabbit hole goes. We begin at our own familiar baseline. A comfortable room on Earth sits at roughly 293 Kelvin. Here, the air molecules are moving at hundreds of miles per hour, bouncing off our skin with energetic abandon. As we descend to the freezing point of water, we reach 273 Kelvin. The world creates ice, but the atoms within that ice are still incredibly active, vibrating with significant thermal energy. We drop further. At 194 Kelvin, we reach the temperature of dry ice, carbon dioxide freezing into a solid, demolecular. Dance is slowing, but it is far from over. At 77 Kelvin, we encounter liquid nitrogen. Here, the air itself turns into a fluid. The energy is now so low that the violent gas molecules we breathe have lost the will to fly apart. They clump together, rolling and sliding in a supercool stream. To a human, this temperature is lethal and instant. To the universe, it is still relatively warm. We must go deeper. We descend into the single digits. We pass the liquefaction point of hydrogen, the fuel of stars, which turns into a liquid at 20 Kelvin. We are now entering the realm of deep space. The background temperature of the universe, the climate of the void we explored earlier, sits at 2.7 Kelvin. This is the baseline hum of the cosmos, the heat left over from the Big Bang. At this level, the vibration of matter is barely a whisper. The atoms are almost comatose, possessing only the faintest ghost of energy. But 2.7 Kelvin is not 0. There is still a gap. There is still a tiny distance between the cold of space and the ultimate floor. As we push our imagination into this final sliver of the thermometer from 2 Kelvin to 1 Kelvin, to the fractions of a degree, we enter a strange and delicate borderland. We are approaching the limit of physics itself. In this final descent, the classical rules of the world begin to dissolve. As atoms approach the state of total stillness, they begin to lose their individual identities. They start to overlap, blurring into one another. The distinct jostling crowd of particles merges into a single quantum entity, moving in unison. This is the realm of superfluids and superconductors, where the friction of reality disappears because the chaos of heat has been removed. They had not been scooped by a rival theory, but by the physical reality of the universe itself. Penzias and Wilson had not found a defect in their antenna. They had found the afterglow of creation. They had accidentally stumbled upon the oldest light in existence, a fossil of energy that had been traveling toward Earth for billions of years. The noise that they had tried so hard to scrub away was, in fact, the thermal signature of the cosmos. It was the measurement that would transform cosmology from a branch of philosophy into a branch of precision science. This moment defined the transition from the unknown to the measured. The temperature of space was no longer a theoretical 0 or a vague guess. It was a tangible, recordable signal. The vacuum was not empty. It was filled with a sea of photons that carried the temperature of the past into the present. To understand why this temperature is so cold, why the fire of the Big Bang appears to us now as a freezing whisper, we must look at what happens to light when it is forced to travel across the expanding fabric of space-time. We must understand the mechanism of the redshift, the process that cools the universe. For decades after the discovery of the cosmic microwave background, the universe presented astronomers with a riddle wrapped in a contradiction. Penzias and Wilson had found the afterglow of creation, and it was magnificent in its consistency. No matter where they looked, the temperature of the cosmos appeared to be exactly the same, 2.725 Kelvin. It was a smooth, unbroken wall of microwave. Static, a testament to a birth that was incredibly uniform to the instruments of the 1960s and 70s. The early universe looked like a pristine ocean of energy, perfectly level and undisturbed, but this perfection was a problem. In fact, it was a catastrophe for our understanding of existence. If the infant universe was truly as smooth as it looked, then we should not be here. A perfectly uniform distribution of matter and energy means that the pull of gravity is equal in all directions. In such a balanced world, no atom is pulled closer to any other atom. Gas does not clump. Dust does not gather. The universe would simply expand forever as a featureless, thinning soup of particles, never forming a single star, never spiraling into a single galaxy, and certainly never coalescing into the rocky silence of a planet. The existence of the complex, structure-filled universe we see today, the tapestry of galaxy clusters, filaments, and voids demanded that the early universe was not perfect. Somewhere in that smooth wall of background static, there had to be flaws. There had to be wrinkles, tiny deviations in density where gravity could gain a foothold. There had to be seeds, and so, the scientific community began a new quest. They stopped listening for the mere presence of the heat and started searching for the imperfections within it. They were looking for variations so subtle that they were buried beneath the noise of the atmosphere and the hum of their own electronics. To find them, humanity had to leave the surface of the Earth. We had to lift our sensors above the water vapor and the thermal interference of our planet and place them in the cold clarity of the vacuum itself. In 1989, NASA launched the Cosmic Background Explorer, known as COBE. Its mission was to map the entire sky in microwave light with unprecedented sensitivity. For 2 years, the satellite scanned the heavens, building a thermal portrait of the universe as it appeared, 380,000 years after the Big Bang. The data it returned was initially terrifying in its smoothness. The curve of radiation matched the theoretical predictions of a perfect black body radiator so precisely that when the chart was shown at a conference, the room erupted in a standing ovation. It proved the Big Bang theory was correct, but the smoothness remained. Then, as the team dug deeper into the noise, analyzing millions of measurements, a pattern began to emerge. It was faint, hovering at the very limit of what was detectable, but it was undeniable. The sky was not a single color. It was mottled. COBE revealed that the temperature of space varies. It is not a flat 2.725 Kelvin everywhere. Near our regions, where the temperature dips slightly, by perhaps 30 millionths of a degree, and regions where it rises by a similar infinitesimal amount. These were the anisotropes, the Greek word for not equal in all directions. The map COBE produced was pixelated and bleary, but it showed a universe that was bruised with cold spots and warm spots. It was the first glimpse of the primordial seeds we had been searching for. However, the COBE map was only the beginning. It was a sketch drawn with a broad brush. To truly understand the architecture of these ancient fluctuations, we needed sharper eyes. We needed to bring the baby picture of the universe into high definition. This drive for precision led to the launch of the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001, followed by the European Space Agency's Planck satellite in 2009. These observatories were marvels of cryogenic engineering. To measure the temperature of the universe with an accuracy of millionths of a degree, the instruments themselves had to be cooled to within a fraction of a degree of absolute zero. They had to be colder than the space they were watching, effectively becoming the coldest objects in the solar system, shielding their detectors from the blinding heat of the sun and the earth. The images returned by Planck are among the most important documents in the history of science. When projected onto a flat oval, representing the entire celestial sphere. The map looks like a piece of abstract art, a speckled oval of blue, orange, and yellow splotches. To the casual observer, it looks like random noise, but to the cosmologist, it is a blueprint. Each speck of color on this map represents a temperature difference of mere microkelvins. The blue regions are ever so slightly colder than the average. The red and yellow regions are ever so slightly warmer. But these are not just measurements of heat, they are measurements of destiny. We are looking at a fossil record of sound waves. In the incredibly dense, hot plasma of the infant universe, photons and matter were locked together in a fluid embrace. The universe was ringing like a bell, struck by the violent energy of its own birth. Pressure waves pulsed through the plasma, compressing gas in some areas and rarefying it in others. When the universe expanded and cooled enough for atoms to form the moment of recombination, the fog cliffed, the light broke free, streaming across the cosmos. The pattern of those pressure waves was frozen into that light forever. The warmer spots on the map correspond to regions where the gas was slightly compressed, slightly denser. The cooler spots corresponds to regions where the gas was slightly less dense, slightly more expanded. What we are seeing in the Planck data is a direct observation of the quantum fluctuations of the microscopic early universe, blown up to the size of the entire cosmos. We are seeing the moment when the quantum world imprinted itself onto the macro world. These tiny temperature variations, these ghosts of heat, measuring less than 0.0001 Kelvin, are the reason the universe is not a boring, homogeneous void. New data finally revealed exactly how cold space really is, not just as an average, but in its specific geographies. It transformed the concept of cold from a single number into a landscape. We can now point to a specific patch of the southern sky, known as the cold spot, and say that it is distinct from its neighbors. We can trace a line across the oldest light in the universe and see the mountains and valleys of energy that defined the pre-galactic era. But the true power of this map lies not in the colors themselves, but in what they compelled gravity to do next. The discovery of these fluctuations solved the mystery of our existence, but it also set the stage for a violent and complex struggle. The tiny temperature differences were not static. They were the opening moves in a cosmic game of accumulation. The cold spots and the warm spots were about to dictate the flow of matter for the next 13 billion years. To understand the magnitude of this, we must shift our perspective from the map to the mechanism. We must visualize how a temperature difference of a few microkelvins translates into the formation of a galaxy containing hundreds of billions of stars. We must watch as the universe takes these tiny imperfections and amplifies them through the sheer, relentless persistence of gravity. If we were to step back and view the modern universe from a distance that renders galaxies as mere specks of dust, the first thing we would notice is not the light. We would not be struck by the brilliance of the stars or the neon glow of the nebulae. Instead, we would be overwhelmed by the darkness. The maps produced by the Planck satellite revealed the subtle seeds of structure in the infant cosmos, but 13 billion years of expansion have stretched those seeds into a vast, cavernous web. The universe we inhabit today is not a kingdom of fire. It is an incomprehensibly vast ocean of near absolute zero, dotted with tiny fragile archipelagos of warmth. The human eye is biased toward light. When we look up, we see the moon, the planets, the constellations. We see the energy. We assume that the universe is defined by these bright objects. But in terms of volume, the stars and galaxies are statistically insignificant anomalies. If the universe were the size of the Earth, all the matter within it, every star, planet, black hole, and gas cloud would fit inside a single raindrop. The rest is void. The rest is the deep, pervading cold we have tracked from the beginning of time. This realization forces a shift in how we perceive our place in the thermal history of the cosmos. We live in a rare exception. A star is a rebellion against the natural state of the universe. It is a localized knot of energy that has momentarily refused to succumb to the entropy of the vacuum. To understand the true nature of space, we must leave the comfortable warmth of our solar system and drift into the regions that constitute the majority of reality. The cosmic voids dot between the great filaments of galaxies. Those long, winding rivers of light that thread through the cosmos lie immense chasms of nothingness. These are the cosmic voids, regions spanning hundreds of millions of light years, where galaxies are almost entirely absent. To float in the center of the boat's void, or the Eridanus supervoid, is to experience the closest approximation to absolute isolation that nature allows in these deep waters. The density of matter drops to less than 1 atom per cubic meter. There are no nearby stars to warm the dust. There are no supernovae to inject shockwaves of energy. There is only the fossil radiation of the Big Bang, the 2.7 Kelvin bath of microwaves that permeates every inch of space. Here, the temperature of the environment is the temperature of the universe itself. A thermometer placed in these voids would read the baseline of existence, uncorrupted by any local heat source. It is a realm of supreme stillness, where the thermal history of the cosmos has been allowed to play out without interruption. Yet it is precisely this overwhelming cold that makes the existence of stars possible. In a twist of thermodynamic irony, the universe cannot create fire without first creating ice. The birth of a star, the ultimate engine of heat, requires an environment of profound chill to begin. To understand this paradox, we must journey from the desolate voids to the spiral arms of a galaxy like our own Milky Way. Here, the density of matter is much higher, and the space between the stars is filled with a diffused haze of gas and dust, known as the interstellar medium. But this gas is not ready to form stars. It is too thin, and often too warm. The atoms are moving too fast, buzzing with kinetic energy that resists the pull of gravity. Gravity is a weak force. It struggles to pull tenuous gas clouds together because the internal pressure of the gas, the heat, pushes outward. If a cloud is warm, the atoms bounce off one another, keeping the cloud puffed up and diffuse. For gravity to win the tug-of-war, the cloud must lose its energy. It must cool down. This leads us to the hidden sanctuaries of the galaxy, the giant molecular clef. These are the wombs of the stars, but to the eye, they appear as holes in the sky. If you look at the Milky Way on a clear night, you will see dark patches interrupting the band of starlight, as if someone has spilled ink across the heavens. These are not empty spaces. They are clouds of gas and dust so thick, so dense, that they block the visible light of the stars behind them. Inside these dark nebulae, a profound cooling process is taking place. The outer layers of the cloud act as a shield, absorbing the harsh ultraviolet radiation from the rest of the galaxy. They protect the interior from the starlight that would otherwise heat it up. Deep inside this shadowed realm, shielded from the fires of the galaxy, the temperature drops well below the 2.7 Kelvin background of the universe. No, not quite below, but it approaches a distinct chemical stillness. While the background radiation sets a floor, the dense gas and dust shield the interior from extra heat. The temperature stabilizes around 10 to 20 Kelvin, just a few degrees above absolute zero. But critically, it is cold enough for chemistry to change. In this deep freeze, atoms slow down. Hydrogen pairs up to form molecular hydrogen. Carbon and oxygen find one another to form carbon monoxide. Dust grains accumulate layers of ice. The frantic thermal motion that fights against gravity begins to subside. The pressure drops, and suddenly, gravity gains the upper hand. This is the great cosmic requirement. Only the cold can collapse. A cloud that cannot cool is a cloud that will never shine. It must shed its internal heat to shrink. As gravity pulls the gas inward, the compression naturally generates heat. Think of a bicycle pump heating up as you compress the air. If that heat stayed trapped inside, the pressure would rise and halt the collapse. The star would die before it was born. So, the cloud breathes. It radiates energy away in the form of infrared light and radio waves. Molecules like carbon monoxide act as coolants, absorbing the heat generated by the compression and firing it out into the void as photons. These photons escape the cloud, carrying the thermal energy with them, leaving the gas colder and denser than before. It is a delicate, millions of years long dance between gravity and thermodynamics. The cloud must stay cold enough to keep falling inward, shedding its energy into the vast heat sink of the surrounding vacuum. The vacuum, with its infinite capacity to absorb radiation, acts as the ultimate disposal system for the cloud's excess heat. Without the deep cold of space to accept this energy, the heat would build up, and the cloud would stabilize as a warm puff of gas, never igniting into a sun. Thus, every star we see in the night sky is a testament to the cooling power of the universe. The sun exists only because, 5 billion years ago, a dark, freezing cloud was able to dump its thermal energy into the cold void fast enough to collapse under its own weight. The fire of the star is the final result of a long, cold victory by gravity. But these molecular clouds are not just uniform blankets of cold. They are textured, turbulent landscapes. As we drift deeper into one of these stellar nurseries, the pillars of creation or the Orion molecular cloud, we find that the distribution of cold is not even. There are cores of incredible density, porks where the dust is so thick that the temperature drops even further, creating the perfect conditions for the violent process of protostar formation. In these dense cores, the contrast is stark. You have a region of space that is hovering near absolute zero, a pocket of silence and shadow. And yet, right in the center, the pressure is mounting. The collapse is accelerating. The temperature is beginning to spike, not from external radiation, but from the sheer friction of infalling matter. We are witnessing the transition from the coldest places in the galaxy to the hottest dot. This interplay creates a universe of extremes. There is no middle ground. The matter is either dispersed in the freezing void, drifting aimlessly in the dark, or it is crushed into the searing fusion reactors of stars. The average temperature of the universe may be 2.7 Kelvin, but almost no matter actually exists at that temperature. The matter is either huddled in the frozen nebulae or burning in the stellar furnaces. This thermal segregation tells us something profound about the structure of reality. The universe is not a smooth blend of temperatures. It is a system of barriers. The vacuum insulates the stars from one another, allowing them to burn for billions of years without heating up the space between them. If space were a conductor, if it were filled with air, the heat of the stars would bleed out, the clouds would warm up, and the cycle of star formation would grind to a halt. The cold voids are not just wasted space. They are the necessary reservoirs that allow the thermodynamic engine of the cosmos to function. As we survey these islands of warmth, these galaxies spinning in the dark, we must recognize how fragile they are. They are besieged by the cold. They are losing energy every second. The light that streams from every star is energy leaving the system, traveling out into the expanding emptiness, thinning out, cooling down, and eventually becoming indistinguishable from the background hiss. The universe is slowly processing its fuel, turning mass into light and light into stretched, cold radiation. But before we look to the ultimate end of this process, we must look at the exceptions to the rule. We have seen how cold clouds create hot stars, but does nature ever work in reverse? Is it possible for the violence of a star to create a region of space that is even colder than the empty void itself? Can a natural object defy the 2.7 Kelvin background and plunge closer to absolute zero than the ghost of the Big Bang? To answer this, we must leave the stellar nurseries and turn our attention to the dying breath of a star. We must find a place where the expansion of gas is so rapid, so violent, that it freezes the very space it occupies. We are looking for the coldest, natural place in the universe. Throughout this journey, we have established a fundamental law of the cosmic environment. The universe has a temperature floor. We have learned that the vacuum is not empty, but filled with the relic radiation of the Big Bang, a bath of photons. That keeps the ambient temperature of space fixed at roughly 2.7 Kelvin. In the deep logic of thermodynamics, this number serves as a boundary. Any object left to drift in the void, isolated and passive, should eventually settle at this temperature. It is the equilibrium point, the state of rest where the energy coming in matches the energy going out. To go lower, to become colder than space itself, should require technology. It should require the active, artificial pumping of heat that we perform in our cryogenics laboratories on Earth. Nature, by all accounts, should not be able to break its own baseline, and yet, in the constellation of Centaurus, some 5,000 light-years from Earth, there is a ghost that defies this rule. Drifting against the backdrop of the Milky Way is a ghostly, double-lobed cloud of gas that glows with a faint, spectral light. It is known as the Boomerang Nebula. To the eye of the Hubble Space Telescope, it appears as a bow tie of shimmering dust, a delicate structure of reflected starlight. But to the submillimeter telescopes that can sense the vibration of cold matter, it stands out as a glaring anomaly. It is a hole in the thermal fabric of the galaxy dot. The temperature of the Boomerang Nebula has been measured at 1 degree Kelvin. It is approximately minus 272 degrees Celsius, or minus 458 degrees Fahrenheit. It is colder than the empty void that surrounds it. It is colder than the shadowed craters of Pluto. It is colder than the deepest recesses of the giant molecular clouds where stars are born. In fact, it is the only natural object ever observed that has managed to drop below the temperature of the cosmic microwave background. If you were to float inside this nebula, the warmth of the surrounding universe, the 2.7 Kelvin afterglow, would actually attempt to heat you up. A nebula is a refrigerator running in the middle of a glacier. To understand how this is possible, we must look beyond the passive cooling of radiation we discussed in previous chapters. The stone floating in space cools down by shedding light, a slow and gentle process. But the Boomerang Nebula is not a stone, and it is not passive. It is a violent machine. It is a system in the throes of a dramatic transformation, and it is achieving its extreme temperature through a mechanism of physics known as adiabatic expansion. The term adiabatic comes from the Greek for impassible. In thermodynamics, it refers to a process that happens so quickly or in such isolation that no heat is transferred into or out of the system from the outside world. The system is cut off, forced to rely entirely on its own internal energy resources. Consider the physics of a gas. We know that temperature is the measure of the average speed of the atoms moving within that gas. But what happens when that gas is forced to expand? Imagine a balloon filled with air. The molecules inside are bouncing off the rubber walls, exerting pressure. If we allow the balloon to expand, the walls move outward. The molecules must push against the retreating walls to fill the new volume. In physics, this pushing is defined as work. Work requires energy. But where does the gas get the energy to push the walls of the balloon outward? It cannot borrow it from the outside world if the expansion is fast enough. It must pay for this expansion from its own pockets. It uses its own kinetic energy, the very motion of its atoms, to do the work. As the atoms spend their energy pushing outward, they slow down. And as we know, when atoms slow down, the temperature drops. We experience this phenomenon in our daily lives, though often without realizing it. When you press the nozzle of a spray can, be it deodorant, paint, or compressed air, the can feels instantly cold to the touch. The gas inside the can is under high pressure. When the valve opens, the gas rushes out into the lower pressure of the room. It expands violently. In that fraction of a second, the gas molecules are doing tremendous work to push the atmosphere out of their way. They consume their own heat to fuel their escape, and the result is a sudden, sharp drop in temperature. The Boomerang Nebula is a cosmic spray can on a scale that defies comprehension. At its center lies a dying star, a red giant that has reached the end of its life. It has burned through its hydrogen fuel and is now shedding its outer layers in a catastrophic wind. But this is not a gentle breeze, for reasons that astronomers are still unraveling, likely involving a smaller companion star interacting with the dying giant. The gas is being ejected at phenomenally high speeds. This stellar wind is blasting outward at nearly 164 kilometers per second, over 360,000 miles per hour. It is moving 10 times faster than the winds of a typical dying star. This ultra-fast stream of gas is punching out into the surrounding vacuum, expanding rapidly as it leaves the gravitational grip of the star. Because the expansion is so explosive, the gas does not have time to absorb heat from the surrounding starlight or the cosmic background radiation. It is thermally isolated by its own speed. The gas molecules are expending their internal kinetic energy at a furious rate to drive the expansion, pushing against the tenuous medium of space and against their own gravitational history. As they rush outward, they sacrifice their heat for volume. This process is so efficient, so relentless, that it has driven the temperature of the gas down past the equilibrium of the universe. It has smashed through the 2.7 Kelvin floor and plummeted to 1 Kelvin. It is a momentary triumph of dynamics over thermodynamics. The star is creating a localized bubble of winter that is deeper than the winter of the cosmos itself. However, this deep freeze is a fleeting condition. In the vast timescales of astronomy, the Boomerang Nebula is a blink of an eye. It is a pre-planetary nebula, a brief transitional phase that lasts perhaps only a few thousand years. Soon, the central star will shed its disguise and reveal itself as a searingly hot white dwarf. Its intense ultraviolet radiation will flood the expanding gas, ionizing it and causing it to glow as a true planetary nebula. The heat will return, the gas will slow, and the equilibrium will be restored. The nebula will warm up to meet the ambient temperature of space, and the anomaly will vanish. But for now, it stands as a testament to the power of expansion. It reinforces a crucial concept in our understanding of the universe. Temperature is tied inextricably to space itself. When space expands, whether it is the local space of a gas cloud or the metric expansion of the universe, energy is diluted. This mechanism of adiabatic cooling is not just a curiosity found in a single nebula. It is the fundamental reason why the universe is cold in the first place. The Boomerang Nebula is a microcosm of the Big Bang's aftermath. As we look at this dying star, we are seeing a small-scale replay of the cosmic history we explored in earlier chapters. The universe itself began as a fireball of infinite heat. It cooled down not because it lost heat to something outside. There is no outside, but because it expanded. It did work against its own gravity, stretching the wavelengths of its own light, spending its energy to buy size. The Boomerang Nebula serves as a laboratory for the extreme. It shows us that the rules of thermal equilibrium are not absolute chains. They are tendencies that can be temporarily broken by violent forces. It reminds us that cold is not just a passive state of waiting. It can be actively manufactured by the chaotic death throes of a sun. As we linger in this freezing cloud, observing the ghostly lobes stretching out into the darkness, we must consider the implications of such extreme cold. At 1 degree Kelvin, we are skirting the edges of physics where matter behaves in ways that violate our classical intuition. We are close to the realm where atoms should stop completely, yet here they are, rushing outward at hundreds of thousands of miles per hour. This juxtaposition of high speed and low temperature highlights the difference between the bulk motion of a gas and the random motion of its atoms. The cloud as a whole is moving fast, but the individual atoms within the cloud, relative to each other, are incredibly still. They are flying in formation, a synchronized army of particles marching into the void. But what does this anomaly tell us about the future? If a dying star can create a pocket of cold deeper than the background universe, could the universe itself eventually cool below its current 2.7 Kelvin floor? Is the 1 Kelvin temperature of the Boomerang Nebula a glimpse of the destiny that awaits everything? To answer this, we must look at the relationship between the expansion of space and the flow of time. We must understand that the Boomerang Nebula is not just a freak accident. It is a preview. The temperature of the cosmos is not a fixed setting on a dial. It is a coordinate in time. Throughout our journey, we have measured the cold as a static condition, the freezing void, the insulated vacuum, the baseline hum of 2.7 Kelvin. But this number is not permanent. It is merely the current reading on a thermometer that has been falling for 13.8 billion years. To understand the true nature of space, we must see this temperature not as a state, but as a trajectory. We must look at the cold as an arrow, flying straight and true from the heart of a primordial fire toward a future of infinite ice. When we look at the thermometer of the universe, we are looking at a clock. Every drop in temperature corresponds to the passing of eons. The physics governing this descent are elegant and unforgiving, binding the concepts of space, time, and heat into a single, unbreakable relationship. This relationship is defined by the expansion of the universe. Imagine the cosmos in its earliest infancy, mere fractions of a second after the moment of inception. At this stage, the universe was not a vast, dark void dotted with stars. It was a singularity of unimaginable density, a speck of existence smaller than a proton, yet containing all the energy that would ever exist. In this compressed state, the concept of cold was meaningless. The temperature was the Planck temperature, a theoretical ceiling of heat so intense, roughly 1 million degrees, that the fundamental forces of nature were fused together. It was a realm where physics as we know it could not function. Then, the expansion began. Space did not expand into anything. Space itself stretched, and as it stretched, it cooled. It is the same principle we observed in the Boomerang Nebula, but applied to the entirety of existence. The universe acted like a colossal gas cloud, doing work against its own gravity, spending its energy to buy size. As the universe doubled in size, its temperature plummeted. It fell from the incomprehensible highs of the Planck era down to the billions of degrees. This was the era of the primordial plasma, a soup of subatomic particles so hot that they smashed into one another with blinding violence. Protons and neutrons formed, only to be blasted apart by high-energy photons. It was a universe of pure noise and light, too hot for structure, too hot for silence. We can trace this cooling curve with precision. It is a slide that moves through specific epochs, each defined by a threshold of heat. As the temperature dropped below 10 billion Kelvin, the violence subsided just enough for the nuclei of helium and lithium to form the first stable elements. But it was still an inferno. The universe remained an opaque fog of plasma for hundreds of thousands of years, a glowing trap where light could travel no more than a few inches before crashing into an electron. Then came the great decoupling. This is the moment, 380,000 years after the beginning, when the temperature finally dipped below 3000 Kelvin. To a human, 3000 Kelvin is still searing. It is the temperature of a welding arc or the surface of a red dwarf star. But to the universe, it was a cold snap. It was the critical point where electrons slowed down enough to be captured by atomic nuclei. Suddenly, the fog lifted. The free electrons were swept up into neutral atoms. The path for light cleared. The photons that had been trapped in the plasma were released, streaming out into the newly transparent void. This is the light we see today as the cosmic microwave background. At the moment of its release, this light was not microwave radiation. It was visible, orange-red light, blazing with the heat of a dying star. The entire universe glowed like the embers of a fire. But the expansion did not stop. It continued, relentless and steady. As space stretched, it stretched the light traveling through it. The wavelengths of those orange photons were pulled longer and longer. Red light became infrared. Infrared became radio. As the wavelength increased, the energy decreased. The universe dimmed. This is the mechanism of the cosmic clock. The expansion of space dilutes the energy density of radiation. If you take a box full of photons and double its size, the densities of the energy drops. The temperature falls. For the next 100 million years, the dark ages, the universe continued to cool in silence. There were no stars yet to light the dark, only the fading afterglow of the Big Bang shifting into the invisible infrared. The temperature dropped from thousands of degrees to hundreds, then down to double digits. The universe became a truly cold place for the first time. It became a graveyard of neutral hydrogen gas, waiting for gravity to wake it up. By the time the first stars ignited, ending the dark ages, the background temperature had already fallen to roughly 50 Kelvin. It was cold, but compared to today, it was a tropical paradise. The universe was smaller then, more compact, and the heat of creation was still fresh in its memory. Today, billions of years later, we measure the temperature at 2.725 Kelvin. This number is not random. It is the precise value predicted by the mathematics of a universe that has expanded by a factor of 1,100 since the time of recombination. The new data from our satellites does not just give us a snapshot of the sky. It gives us a confirmation of the timeline. The cooling rate matches the expansion rate perfectly. If the universe were static, if it were an eternal, unchanging box, the temperature should have remained constant. Or, if the universe were contracting, the temperature should be rising, turning the cosmos into an oven. The fact that we measure this specific, low temperature is the strongest thermodynamic proof we have that we live in an expanding reality. We are riding a wave of cooling that has not yet crashed. This trajectory reveals a profound truth about the arrow of time. Time is often described as the increase of entropy, the tendency for order to dissolve into disorder. But in the context of the cosmos, time is also the dilution of heat. The past is hot. The future is cold. We can determine the age of the universe simply by taking its temperature. If we were to travel back in time 1 billion years, we would find a universe that was slightly warmer, perhaps 3 Kelvin. If we traveled back 7 billion years, to the time when dark energy began to accelerate the expansion, the universe would have been noticeably warmer, perhaps around 4 or 5 Kelvin. This difference seems trivial to us, but for the delicate chemistry of gas clouds, it matters. It means that star formation in the early universe took place in a warmer bath. The molecular clouds had to work harder to cool down. The thermodynamics of the past were slightly different, favoring the creation of massive, short-lived stars. Conversely, looking forward, the arrow points only one way. The expansion is stretching the gap between galaxies, creating more and more void. As the volume of the universe increases, the density of the photons decreases. The 2.7 Kelvin we measure today is a fleeting value. It is the temperature of our moment, our epoch. Every second, the universe gets a little bigger and a little colder. The wavelengths of the ancient light are being stretched thinner and thinner. The photons are losing energy, becoming more lethargic, shifting deeper into the radio spectrum. We are witnessing the slow freezing of the cosmos. This concept of a cooling timeline allows us to place ourselves in context. We are living in a Goldilocks era of cosmic history. We are far enough from the Big Bang that the universe has cooled sufficiently to allow complex chemistry and solid matter to exist. The screaming radiation of the early epochs has faded to a harmless whisper. Yet, we are not so far in the future that the universe has frozen over completely. We still have stars. We still have active galaxies. We still have heat. We exist in the intermediate phase, the long, slow afternoon of the universe's lifespan. The violent morning is over, but the cold night has not yet fully set in. The temperature of space is low, but not yet zero. However, the connection between expansion and cooling raises a disturbing question. If the universe is expanding, and the expansion is accelerating, what happens to the temperature in the deep future? If the clock keeps ticking, does it ever stop? Does the temperature graph eventually flatten out, or does it plunge forever into an abyss of infinite cold? To answer this, we must project the arrow of expansion forward. We must use the data we have gathered, the cooling rate, the acceleration of dark energy, the density of matter to model the climate of the future. We must envision a time when the 2.7 Kelvin background has faded to 1 Kelvin, then to 0.1 Kelvin, and beyond. As we stare down this trajectory, we begin to see the ultimate destination of the arrow. The cooling of the universe is not just a side effect of expansion, it is the driver of destiny. The drop in temperature dictates the lifespan of stars, the stability of galaxies, and the possibility of life. The universe is a heat engine that is slowly running out of steam. It is expanding its piston space itself, and in doing so, it is exhausting its capacity to do work. The cold we feel today is just the beginning of a much deeper, more permanent winter. If the history of the universe were written as a biographer, we would currently be living in the prime of its life. We exist in the stelliferous era, the age of stars. It is a time defined by activity, by the vigorous burning of hydrogen, the spiraling dance of galaxies, and the constant, energetic exchange of light. To us, looking up from our warm, rocky platform, the cosmos appears inexorable. The night sky is a tapestry of diamond-hard brilliance that seems as if it will endure forever. But the data we have gathered, the cooling curve of the background, radiation, the accelerating expansion of the voids, and the laws of thermodynamics tells a different story.